Hello, welcome back to Math 332 Linear Algebra. We are going to continue our discussions on the geometry on our end and develop a few more theorems and necessary tools and concepts before we go to develop the theory for the least square methods, which is the last thing we're going to do for this course. So let's do a very quick review of the things that we have seen before in the previous video and the things that is going to be needed actually for this particular discussion here today. So of course, we already know what dot products for two vectors are, and we know that one of the main things to use dot products is to use it to identify when the two vectors are orthogonal to each other's, right, perpendicular to each other's. And we also use dot products to develop the projection formula. So we take a vectors x, and then we have a vectors a, and we are looking for how much of the vector x is actually on a. So how much of the vector x is actually on a is given by that. And we actually went through the discussions, the derivations in the previous video, which is very simple. If you want to figure out how much of the vector x is on A, so that particular vectors must have a magnitude and the directions. So the direction here is on A, obviously. So this direction is going to be on the directions of A. So this is unit vectors of the vector A, which give you the directions, and this is the magnitude, which basically means what is the length of this vectors right here. So we figured it out, and that's not very difficult to do. And we also look at these vectors, x minus the projections, and this particular vectors and the projection vectors, they are actually orthogonal to each other. I'm coming out kind of like jumping the gun here, but I already have a 90 degrees right here indicating that they are orthogonal. But if you look at the notes, you actually see that we derive that. We know that particular facts by taking the dot products of this vectors and this vectors and show it equal to 0. And the whole point of doing this is that we want to be able to write a vectors as a sum of two different vectors. So we write x as a projection of x onto A plus this vectors. Obviously, you can see algebraically this cancels. So obviously, we're just having x. And you might wonder, why do we want to write it like this? We want to write it like this for applications that unfortunately you don't really see a lot in this course because we don't do it. But the nice things about writing it like that is that we basically decompose these particular vectors into two parts, and these two parts are orthogonal to each other. These two parts are perpendicular to each other. And today we're going to see one of the generalization of this particular observation here is called the orthogonal decomposition theorem. That's one of the main things that we want to prove today. And obviously, we also review the concept of orthogonal complements of a vector space, and we have the fundamental theorem of linear algebra, which basically says that the row space and the null space, they are orthogonal complement of each other. Same with the column space and the null space of A transpose. And we also prove very simple and nice theorems that says that for any vector space W, if you look at its orthogonal complements and you try to look for the same the common elements between these two vector space, and you'll figure out that the only common elements for those two vector space are the zero vectors. So this is what we proved last time. And we also have a video on the concept of orthogonal basis. So orthogonal basis is the basis, they are same concept as basis of a vector space, where they have to span the space and they are linearly independent. But we actually have a requirements that now they are actually orthogonal. There's all these vectors are orthogonal to each other. Orthogonal to each other means that if you take any vectors ui from these collections and any vectors uj from these collections, if you take the dot products, it will be 0 if your I and j are different. And if your I and j is the same, which means you take the dot products with the vector itself, then you will get a non-zero numbers. So this will be the orthogonal basis. And one of the fun thing about having orthogonal basis is that you can figure out some of the things pretty easily. So for example, if you have W, okay, let's say just make the things easier for our discussion here. So we can kind of like just look at R2, for example. So in R2, so obviously one of the orthogonal bases is your standard basis, your I and J. So this is a Y, this is a X. Your I and J is obviously two orthogonal vectors, right? So these are the orthogonal vectors, but you can also find some other orthogonal vectors beside this too. So you can have, let's say, U1 like this, and let's say U2 like this. So these are, again, orthogonal bases. This can be used as orthogonal basis. So you have two orthogonal bases. So you have orthogonal bases consists of two vectors in R2. Let's call them, let's call them u1 and u2, right? So these are the orthogonal bases. So these are orthogonal bases. And if you take a vectors w, okay, that is in R2, so because they are bases, we know that w can be written as c1 of, which is real numbers, all right, u1 plus c2 of u2. And last time, in order to find this u1 and this c1 and c2, you have to solve a system of linear equations to figure this thing out. But if your u1 and u2 is orthogonal to each other, this c1 and c2 is very easy to identify. So you take the dot products of u1, okay, on this left hand side, and that means that you are doing the same thing here. You are taking the dot products of u1 right here. So distributions distribute these properties of dot products. So you will have c1 u1, okay, dot u1, and then plus c2 u2 dot u1. And because they're orthogonal, this part here is 0. This part here is non-zero. So you can see that c1 immediately is w dot u1, okay, over u1 dot u1 is the magnitude of u1 squared. So you can identify c1 pretty easily like that without doing any row reductions and stuff like that. So if you have orthogonal basis, w is going to be c1 of u1 plus c2 of u2. Okay, they are bases, so any vectors w can be written as a linear combination of u1, u2, and we know exactly what is the c1. So c1 is actually w dot u1, okay, over the magnitudes of u1 squared. So again, this is a number. This whole thing is a number, okay, and then u1 plus w dot u2, right, over the magnitude of u2 square. This is again a number, and then you have that. So we know that for any w, you can write it as a linear combination of u1 and u2 because they're bases, and because they are orthogonal bases, we can get the c1 and c2 pretty easily. And if you remember from the previous video, if you require that not only the dot products between different vectors are 0, but the dot product with itself is 1, that's called the orthonormal basis. So orthonormal basis is the one that is normalized in such a way that your vectors has magnitude 1. So your u1's dot u1 here, if it is 0, if it is 1, then you have orthonormal basis, and orthonormal basis will make this expression even easier because this is just 1. So you have that like this, and this is just 1, so you have it like that. So that's the concept of orthogonal basis. So we're going to do all that today. We're going to use all this thing today, and we are basically just going to do two different things today. So one of it is to go through the theorem called the orthogonal decomposition theorem, and another one is going to talk about projections, orthogonal projections, and this is the two things we want to talk about, and then we will be done with it. And all these things that we're going to talk about today, especially the orthogonal projections derivation of this particular concept, is critical in the development of the theory for the least square method. So let's get right to it. So, okay. All right. So let's look at the concept of orthogonal projections. So we have seen a version of projections before, and we have been doing this a lot of times. So let's say that one more time. So you have two vectors, x and a. So we want to figure out, okay, what is the portion of the vector x that is on a. So we want to figure out how much of the x is actually on a, and that is given by the projections of x onto a. That's the notations, and this is x dot a, right, over the magnitudes of a squared and times this vectors a. So this is what we have been doing. This is actually something that we have seen long time ago in the homework. And so that's a projection of a vector x onto a. But right now, what we want to do is different. We are not doing this anymore. We are doing something more sophisticated. So we still have a vector x. Okay, so we still have a vector x. But this vector x is they're all in Rn. And now if you select a vector subspace of Rn, let's say this is W, obviously this is just a graphical representation. It's not all subspaces looks like just plain like that, but it's for the expositions for these things to be easier explained and to represent graphically. I'm going to write this vector space, represent it as kind of like a plane. So you have this W, which is a vector space, and now I am trying to project the vector x onto this space, which means I want to know how how much of the vector x that is on W. So I kind of need to know like what is this. So this obviously is going to be a vector that's on W, all right? And I want to know how much of the x that is actually on that vector space W. So notation wise, nothing's changed. So this is going to be the projections of x, okay, onto this vector space W now. Okay, so notation wise it's the same. Last time we put this as a vector A, but now this is not a vector, but it's a space. Okay, so in order to make sure that you don't confuse with all the notation here, so in this notes right here, we are saying this as a vector V. That's okay, so let's just change it. So this is vector V. Okay, so now we are looking at the projection of V onto W. And in order to make all this thing easier, we are also have to figure out what is the basis for this vector space, W. It's a subspace of Rn. So here we are given a collection of bases, a basis which is orthogonal basis. So these are not just any bases that we have seen before. These are bases that are orthogonal to each other. And so let's say we have all that. And then the definition is that the projection of V onto W is actually given by the whole bunch of summations, which involve all these terms that kind of looks very familiar, because these are the terms that we've seen before. Last time it's kind of like the things that you project onto a vector U1. So if you have a vector project onto vector U1, it kind of looks like this. So it's a sum of little things like that that kind of looks very familiar. And so this is given as a definition. It says that if you have a vector V and you want to project it into vector space W, and if you already have a basis, orthogonal basis for W, and those orthogonal bases is U1, U2, all the way to UK, so the projections of V onto W will look like this. Now, there's a way to see this, why this is true. So you can, I'm going to kind of give a motivation that why you have such a formula is right here. And the thing is actually pretty simple. So you are basically kind of like forcing yourself. You're trying to like, hey, this is V. V maybe is not on W, but if I want to force it, so this is kind of like forcing it, okay? So you try to like forcing it to be on W. So if it is on W, if it is on W, these are bases, right? So if this is a vector that's on W, you want to find out how many of the V that's on here. So this thing that's on W, can be written as a linear combinations of this basis vectors. So this will be like C1 U1 plus C2 U2, so on and so forth. So I'm going to just imagine that we only have U1 and U2 so that I don't have to keep writing, just for simplicity. But obviously, if this is all the way to UK, you can just add a few more terms to write all the way to UK. So the idea is, so let's say this is only, that's here in our case here, you have two orthogonal bases. So this is a basis, orthogonal basis has two vectors, U1 and U2. So this is V. V from this picture is obviously not on W. I purposely draw it like that so that you can see that V is not on W. So the thing that is on W, okay, will have to be like this. Okay, so so what is the things of V that is on W? So you kind of like want to force the V to be on W. So you write like this so that they are on W, because these are the vectors that's on W. So if you force it like that, the question is what is C1 and C2? So you already seen how to find all this. So if you do want to figure out what is C1 and C2, so you again take the dot products with U1, then this thing will be canceled out because they're 0. So you will see that if you really want to force it like that, your C1 will be V dot U1 over U1 square, the magnitude of U1 vectors and U1, and then V dot U2, okay, and then over U2, the magnitude of U2 square, and then U2. So that thing that is on W that you force it on is called the projections of V onto W. Okay, so this is projections of vector V onto the vector space W. That's the reason why you have an expression that looks like this. Okay, does it make sense? All right, so this is how we project something onto a vector space now. So one way to think about all these projections is that you kind of like standing up here. So let's say this is really a plane. Let's say this is really a plane. Okay, let me get rid of this. Okay, so, oh, there's so many things that we have to get rid of. Okay. So now, so what is a projection? So let's say this is W. This W is really a plane. Let's say, okay? Okay, so if you want to figure out how much of the V that is on W, you can imagine that you stand right on top of it, and you can shine a torchlight right on top of it, and and V, think of V as like a solid object, then it started to cast a shadow right here, and that shadow is going to be the projection of V onto W. But when you do this casting the shadow business, your torchlight, nowadays probably you don't have a torchlight, but you have an iPhone, and you switch on the light, so the lights coming from your iPhone will hit this solid object V, and it will cast a shadow. That shadow is a projection of V onto W. You can think of it like that. Okay, so what we want to do next is that once we know all these formulas on how to compute the projections formulas, so always remember though, these formulas that is given right here, you have this formula because we have this orthogonal basis. If you don't have this orthogonal basis, you don't get this. Okay, you do not get this. You will get something else that is very difficult to express. Okay, so we require this basis to be orthogonal basis so that the coefficient here is very easy to compute. Okay, so we need to have orthogonal basis. And we talked about in a previous video, what happens if you do not have an orthogonal basis for that vector space, then there's a process called Gram-Smith process that can help you extract a basis that's orthogonal from that vector space. So every vector space or vector subspace, when it comes to that, you can always think of it that it possesses an orthogonal basis. You can always think of that way. You can always find orthogonal basis for any vector space. Okay. All right. So that's that. Now, one more thing that we want to do. Okay. One more thing that we want to do, and we're done with this. Okay. So let's redraw this thing here a little bit. Okay. So right. So we have V. Okay. So we already know that this notationally, this projections business, we have this. Oops. Sorry. So we have this. This is a projection vector. This is a projection vector. This is a notation V onto W. That's right here. So it is very easy for you to see that this vector right here is V, okay, is V minus the projections of V onto W. Okay, so why is that so? Because if you take this vector plus this vector, you'll get V, right? So this vector here is V minus projection of V onto W, if this is projection of V onto W. If you don't see it this way, you can also do something like that. So you say this is a vectors X that you don't know what that thing is. So if you have vector like this plus this, so you have V, so you have this projection vectors. Okay, let's make the notation easier. So let's say this is P, right? That's X. So you can see P plus X is V. P plus X is V. This is how you add vectors. Okay, you've probably seen it first time in physics, and then in Calc 3 and so on and so forth. So what is X? X is V minus P. So your X here, so your X here, your X right here, this vector here is V minus the projections of V onto W. And this is your projections of V onto W. So we have something that looks like that. And what we're going to show is that actually this is going to be 90 degrees right here. What I'm going to show is that this V minus projection of V onto W and the projection of V onto W, they are orthogonal to each other. This is critical. We kind of see a version of this last time, and you see it here. Okay, so last time when you do a projections, you have two vectors. You have vector X and vector A, and when you do the projection of X onto A, that's this vector right here. And then this vector right here is X minus projection of X onto A, and we have seen that they are orthogonal to each other. And how do you show they're orthogonal to each other last time? You take the dot products. So same with here. So we are claiming that these two vectors are orthogonal to each other. And how do you show that? Well, you take the dot products. You always do that. If I ask you to show that two vectors are orthogonal to each other, the only thing you can do is basically take the dot products and see and hope that they will be 0. And that's how you show two vectors are orthogonal to each other. And the way we show it here is that we are not just going to show that this V minus projection of V onto W is orthogonal to projection of V onto W, but we want to show something stronger. That is to say that I want to show that this vectors, okay, is actually orthogonal to everything that is coming from W. So this is the vector subspace W. So I want to show that every vectors in W, every vectors that is in this set W, they are orthogonal to this. So in the terminology that we know is that we are actually able to show that this thing here is actually in W perp. Okay, so projection of V onto W is obviously a vector that is in W. Okay, is one of the vector that's in W. If you take V minus that vectors, which is the projection of V onto W, I can show that actually, in fact, this vectors right here is actually orthogonal to everything that is in W. So if you have vector that's in W, this two will be orthogonal to each other. So if you have another vectors that is on W, this vector here and this vector here is again orthogonal to each other. So in fact, this terms right here is in W perp. So that's what we want to show. And it is actually easy to show because our vector space right here, W, is spanned, right? Our vector space here, W, is spanned by all these orthogonal vectors, U1 all the way to UK. So if you remember in the previous video, if you wanted to show something is in W perp and your W is actually a span of all these vectors, the only thing you need to show that the elements is in W perp is to show that that particular element has a dot product with U1 and dot product with U2 all the way to dot product with UK. All of them is 0. So if you can show that, then you will be able to show that that particular vectors that has dot product with all this U is 0 will be in W perp. So this is again something that we learned from a previous video. So this is exactly what we're going to do now. We are going to look at this projection formulas and we're going to take V minus this projection formulas. Okay, so V minus this projection formulas is given right here. So this is V minus the projection formulas. Okay, V minus the projection formula. This is not equal here. This is minus. Okay, so V minus is projection formulas. And now we take the dot product U1 or U2. Let's imagine that you're taking a UI that's coming from this orthogonal basis. This I could be anything from 1s to K. So if you take this dot products, okay, with this terms right here, you distribute, right? So the first terms that you have is UI dot V, and then you distribute, and then you distribute, and then you distribute. The good thing is that because they are orthogonal, so if this I here is not 1, these terms will not survive after you take the dot products because is dot products of UI and U1 is actually 0. Okay, so the only thing that will survive obviously is the UI terms. So when you distribute, you have this UI dot V, and then when you distribute with this, you actually have 0. You distribute with this, we have 0 until you get back to UI, and then the dot product with this, we're going to give you this number here, and then this here you'll be UI dot UI, which is the UI dot UI. What is it? What is UI dot UI? So UI, okay, dot UI is going to be the magnitude of UI squared. Okay, so that gives you the magnitude of UI squared, and the rest of it, when you distribute again, you get 0. So at the end, what you get is going to be this particular terms right here, UI dot V, and then this particular terms right here, where this part here and this part here will cancel out. Why? Because they are the same numbers. They will cancel out. So you have UI dot V minus UI dot V, that gives you 0. So in fact, this terms here, okay, dot anything dot U1, for example, will be 0. Dot U2, for example, will be 0. Dot U3, for example, will be 0. All the way to UK, you take a dot product, will be 0. So these terms here have a dot product with everything that is in all this W. So this is W is a span of U1 all the way to UK. Why W is a span of all this? Because this is basis. So one of the definition of a basis is has to span the space. And then you can see that the dot product between all these vectors in this basis is 0. So these are all in W. So immediately this gives you that this particular vector here is in W perp. So we are showing something more than that. Obviously, this vector and this vector are orthogonal to each other because this is from W. So this is from W. How do you know that this is from W? This is like one of the trivial questions. Like, why is this vector on W? Because that's how we define it. We are looking at the vector that's projected onto W. And if you look at these terms here, okay, how do you know this is in W? It is obviously in W because there are linear combinations of the vectors in W. And these are vector space. So if you do linear combinations of vectors as in the vector space is closed under those operations. So you are will be in this vector space W. Okay, so that's that. So this is the parts on orthogonal projections. The things that you need to know is that in order to have these projection formulas, make sure you have a orthogonal basis, and the orthogonal projections of V onto W is given by that. And more importantly, is that this vector here, V minus projection of V onto W, is actually in W perp. So it's kind of like the things that we've seen before. So last time you just have two vectors and you have the projections and x minus the projection, and they are orthogonal to each other. And that is basically kind of like the same thing, but instead of projecting it onto a vector A, now we project it onto a subspace, which is slightly more fancier, right? Because now we can project something onto a vector space. And in order to complete this video, there's only one more thing that I want to talk about, which is this. So last time we shows that if you do this kind of projections, you can write your x as a projection vector plus x minus a projection vector. So we call this orthogonal decompositions. We can write a vectors as a sum of two vectors, where these two parts here are 90 degrees to each other. So we are going to do the same thing here with a slightly more sophisticated concept of projection onto a vector space now. And that's the last thing we want to do. So here we have a computational example. You can look at it. It's not very difficult. It's just computational. So you have a vector space W, and then you are actually given the orthogonal basis. So orthogonal basis for this vector space W is given like that, and you're asked to compute a projection. This is just a computational example. You can just look at it and how to compute them. It's nothing really things that I need to talk about right here. Things should be pretty straightforward. Okay, so the last thing I want to talk about is this theorem, orthogonal decomposition. So this is a version, this is a generalization of this particular observation here, which is pretty obvious. Not something that is very difficult. You can look at the picture and you get this directly. So this last theorem here is basically saying the same thing, but it's a little bit more sophisticated. So let's look at what it said, right? So now, again, you have a subspace W, which is a subspace of Rn. So you have a vector V, just like before. And we say that we can write this vector V, okay, as a sum of two vectors. Let's call W and W perp. So these are vectors. So be careful about the notation. This is kind of like abusive notation. So these are vectors. This is a vectors in W. Okay, this notation here indicate that this is a vector. This is in W perp. Okay, so this is a vectors. Okay, so this is a vector. These are all vectors. Okay, so the V is a vectors, W is a vectors, W perp is a vectors. So this is an Rn. Okay, W is a subspace of Rn. So this is a subspace of Rn. This is a subspace of Rn. And obviously, this is also another subspace of Rn, but this is the orthogonal complement for this vector space W. So basically, you are saying that every vectors in Rn can be written as a sum of two vectors. One of it is from a vector space W, and another one is from W perp. That's what it says, okay? If you do not like this notation, you can say that for every V that is in Rn, we can write it as elements that is, let's call it P and Q, okay? Right, this vector P and vector Q, where vector P is from a vector space W and vector Q is from the vector space W perp. That's what it says. So it says that for every vectors V that is in Rn, that is unique. That's one thing that we want to prove. There's only one way you can do it. So if there's a unique vectors W in the vector space W and a unique vectors W perps in this vector space W perp, so that you can write V as a sum of the vectors W plus W perp. So that's what it said. And that is known as the orthogonal decomposition theorem. Okay. So how to prove this? The proof is actually pretty nice. And so before we do that, there's two parts of this theorem, as you know. So first is that we want to show that for every V in Rn, so this is what we're given, right? So we are in Rn. So let's look at the setup one more time. We are in Rn. So you're given a vector space W, okay? And you're also given a vector V that is in Rn. So this is fixed. This is a fixed vector space, okay? One day I given you this, you're not going to change it. Okay, so I am saying, according to this theorem, they claim that V can be written as a vectors W, okay, plus another vectors W perp. This is from vector space W, and this is from vector space W perp. So to show that this is possible, that's the easy part. Because how do we find W? Okay, so we can find W by, okay, so the first part of the theorem is basically looking at, hey, I'm going to suggest to you what W is, okay? So my suggestions is that W is the projections of V onto this vector space W. So this is my W. So I'm claiming that this is going to be my W. Okay. First of all, how do you know that this is a vectors that is in W? How do you know that this is a vectors in W? Well, that's the whole purpose of doing projection onto W. If doing projection onto W, this is obviously in W. So this part is clear. This is a vectors in W. And the other one right here is going to be V minus the projections of V onto W. So the sum is easily, you can see the sum actually give you V. This is easy to see. So algebraically, V is really equals to this thing plus this thing, okay? This vector plus that vectors. So this is from W. And we already showed that this is from W perp, so that's fine. Okay, so definitely we can write a vectors V as a sum of a vector that's in W and another vector that's in W perp. That's easy. So that's the easy part. So the decomposition theorem says that you can do it. Okay, you can find a vectors which is from W and another vectors which is from W perp, and V will be the sum of that two vectors. That is what we have shown. This is what we have shown. Okay, now so we have shown that this is possible, and that's it. We have shown that this is possible. The only things that you need to do is that, hey, this way of writing it, this is the only way you can get to V if you have to make sure that this vector here is from W and this vector here is from W perp. This is the only way you can do it. This is the only way you can do it. This is a unique part. So they say they have a unique vectors W and W perp such that this is written like this. So we want to show that if you can write like this is the only way you can write. That's the uniqueness part. So to prove uniqueness, we always do the same thing, which is suppose you have two different ways of writing it. Okay, so right here. Okay, so suppose you have two different ways of writing this V. So one of it is that we can write V. Okay, so right here, let me write this thing here. So to prove uniqueness, okay, so to prove uniqueness, let's say you have two different ways that you can write the V. So one way is to write this as W plus W perp. Okay, this is one way of writing it. And let's say you have another way of writing that, which is W1 plus W1 perp. Okay, so this is another way you can write V. Same V. This is two are the same V. So let's say we can write this V as a sum of two vectors. One is from W, one is from W perp. And let's say you have another way of writing it. This is in W, and this is also in W perp. So let's say you have two different ways of writing it. So now this two, W plus W perp, okay, will be equals to W1 plus W perp. W1 perp, because these are two vectors V. They are V, so they are equal. So that's what happened right here. Okay, so suppose you have two different ways of writing it, then W1 plus W1 perp and W plus W perp will be equal to each other. Now let's do a very quick algebra. Move this W to here and move this W1 perps to here. So you have W1 minus W, and then you have W perps minus W1 perp. That is just doing a simple algebra. Now, here you're just going to use some things that linear algebra stuff started to come in. So these are two vectors that's on W, right? This is the vectors that's in W. This is the vector that's in W. W is a vector space. So vector space is closed under addition. So if you have two vectors that's coming from W and you add them or you subtract them, this is still going to be in W. So this is an element that's in W. Okay, same thing here. This is an element in W perp. This is an element in W perp. W perp is also a vector space. So vector space is closed under additions. So this is also in W perp. So now you see that this vectors is in W and this vectors are in W perp, and they are the same vectors. So now we see that. So now we have seen that this one here, W1 minus W, is going to be, first of all, this in W. Okay. Second of all, it is equals to something that is in W perp. So this term here is actually in W and W perp. And we proved last time the only thing that is in W and W perp is the zero vectors. So here it will show that this W1 minus W is actually 0. So W1 and W are actually the same thing. That's how we show them. And exactly the same way, you're looking at this part again. So this is in W perp, but that's also in W. So this terms here is simultaneously in W and W perp. So again, this one here is simultaneously, this vectors here is simultaneous in W and W perp, and we already know that the only thing that's in W and W perp is zero vectors. So again, this gives you this two difference equal to 0, and that gives you the W1 and the W1 perp and W perp. This is a perp right here, that they are the same. So which means that if you write V as two different ways, as W plus W perp, this is coming from W, and this is coming from W perp. And you write V as W1 plus W1 perp, okay? Right? This is from W, this is from W perp. Then, these two terms is actually the same terms. These two terms is actually the same terms. So there's only one way you can write. If you write them differently, you are actually writing the same thing. So this is what the orthogonal decomposition theorem say. It says that every vector V can be written as a sum of two vectors. One is from W and one is from W perp. And this is the only way you can write them. And we actually explicitly shown what are the W and W perp. So this is actually what happened right here. So this is actually how you write them. For every vector V, we can write it as a vector for is from W, and there's a vector that's from W perp. And we already proved uniqueness. So no matter how you do it, if you can find another way of writing it, well, it will have to be still like this. So this is the uniqueness part. So you don't have to worry that there's two different ways of writing it. This is the only way, basically, to write a vectors that is from Rn as a sum of two vectors. One of them is in W, and another one is in W perp. And this is how that orthogonal decomposition is. And unfortunately, we would not have time to see how this is actually being applied. But in a lot of cases, it is very critical that you know there's only one way to write something. And this is how this particular theorem is proved. And you can see that the way we prove it utilize the fact that the W and W perps, there's only one common element in it, which is the zero vector. So you kind of like put everything together, and this is a very nice ways to end this particular notes right here. So basically everything comes together, and we have things that is pretty nice. So a quick summary is that what you need to know in particular about these notes, these are all the tools and theories and concepts that we are going to use for the developments of the least square methods. So that's the last section we want to talk about. And in particular, we're going to use a lot of things about the fundamental theorem of linear algebra. We're going to look at orthogonal projections. This is like another big things that we're going to use. And we'll see that all come together in the last sections of this course, which is the least square methods. And we'll see you there. Okay, thank you.